Now, there's some part to your June 2022 P22 paper that I want to go through. So June 2022 P22, okay, this is variant P22. Now you look at question 5. Question 5. So in your current case here, they mentioned that you have light from a laser that is used to produce an interference pattern on the screen as shown in the figure below. So they then mentioned that light of wavelength 660 nanometer is incident normally on two slits that have a separation of 0.44 millimeter. The double slit is parallel to the screen. The perpendicular distance between the double slit and the screen is 1.8 meter. The central bright fringe on the screen is formed at point O. The next dark fringe below point O is formed at point P. The next bright fringe and the next dark fringe below point P are formed at points Q and R respectively. So the one that I want to go through is the state and explain part from part D onwards. Okay. Now here, based on what I mentioned just now, this one is actually a double slit. Okay. So this question here is concerning a double slit. If you look at part D, they mention this. The intensity of light incident on the double slit is increased without changing the frequency. Describe how the appearance of the fringes after this change would be. Is it different from similar to their appearance before the change? Okay, so for your case here, they mention intensity is increased, but we're not changing the frequency. Okay, so what's the significance of all this is that we know that intensity is proportional to amplitude square. This is something that we learn in waves. So when intensity increases, the amplitude would increase and it will be doubled because it's square. Okay, so this is the significance of the first statement. And then after that, when you see that frequency is unchanged, this one would actually tell you wavelength remains constant. Okay, the fact that they told you frequency is unchanged tells you that lambda remains constant. Now, why is this so? You can actually refer to the equation V is equals to F lambda. This one, let me rewrite it. V is equals to F lambda. Now, there's one fact that you need to know. Wave traveling in the same medium will always, same wave traveling in same medium. Okay, let me just modify this a little. If you have that same wave that's traveling in the same medium, same wave traveling in same medium will always have same speed. Okay, for example, let's just say sound wave traveling through the air. If you're still moving towards in air all the time, the speed is the same. But let's just say the sound suddenly goes through water, it's a different medium now, the speed would change. Okay, or if let's just say it tries to pass through glass, glass is also another medium, so the speed again would change. That's what I mean by same wave traveling in the same medium will always have the same speed. Your speed will only change when you change medium. Okay, so here I can say V is constant because your light is still traveling through air. It isn't really traveling through any other medium. The V here is constant. Okay, so V is constant. Now you look at equation V is equals to F lambda. The question specifically mentioned frequency is constant here, and I also explained that speed is constant, right? So V and F constant, therefore lambda is constant. All right, so wavelength here actually did not change at all by virtue of the frequency being the same. Okay, so now given these two information here, how would your fringe look like after you made those changes? Would it be similar or would it be different? So this one, you can actually kind of refer back to the diagram here. This one is for your double slit. Now, let's just say, for example, your double slit right now. For your double slit, at point of constructive interference at your bright fringe, point of constructive interference or bright fringe, maybe I just write it simple for you. If you look at the point where you have a bright fringe, where you have constructive interference, the general idea is that, let's just say I look at this part here, this bright fringe right over here. The general idea here is that if you get a bright fringe here, it is due to the fact that wave from this source comes here and wave from this source comes here, and they meet constructively to give you a even larger wave. So because it's an even larger wave here means even larger amplitude, okay? So if it's having an even larger amplitude, it will have an even larger intensity, it will appear much brighter. So you're trying to draw out the graph for that, you typically will get something like this. Trying to draw it nicely here. So just bear with me a little because I'm trying to draw everything nicely here. Okay, so let's just say that this is wave from the two sources here is S1 and this is S2. Okay, so wave from S1, when it hits the point where you have a bright fringe, it probably looks like this. Okay, wave from S2, when it comes to this point where you have a bright fringe, it also looks like this right now. Okay, so this one, consider this as having amplitude A, having amplitude A. So when they meet together constructively, you expect to see something that looks like this right now. So let me just draw a graph here. You expect to see something that looks like this. This one would be this. This one, you're going to get an amplitude of 2A. Because your amplitude is larger, you have larger intensity, it appears to be particularly bright. Okay, this is for constructive interference. Now, for the part where they told you that intensity of light is now increased, what does having a larger intensity of light here do to your bright fringe? So if you're talking about the intensity of light now being bigger, just now I mentioned to you early on, if intensity increase, amplitude will become larger, isn't it? So here, you can think of it as this now. The waves from S1 and S2 will still meet at this point to give you constructive interference, but because your intensity of light is actually larger, your amplitude of the individual waves is also actually larger now. So it could probably look like this right over here. So let me just try and draw it nicely again using some separate colors. It could be that maybe you are getting a new wave that looks like this. This one here is probably 1.5 A because you're having larger intensity, so your amplitude is larger. And then the same goes for the wave from S2 also. So this one again is 1.5 A. So if they meet constructively, you're going to get an even larger wave, a wave with a larger amplitude. It will probably look like this now. This is your new wave. Okay, so your amplitude now is 3A. Okay, so here with larger intensity, okay, maybe it's better if I just write it here. This one here, I can say that with larger intensity, amplitude of resultant wave is larger. That one is actually shown by this one. And this one is, if my intensity is larger now, this one is giving me a larger amplitude. With larger intensity, amplitude of resultant wave is larger. So resultant intensity is even larger because amplitude is related to intensity, okay? So with larger intensity use, the amplitude of resultant wave is larger and resultant intensity is also larger. So from here, you can actually say that, therefore, your bright fringe appears brighter. Okay, because your resultant amplitude, resultant intensity is much larger now. Okay, so your bright fringe becomes even brighter. So that is one change that you can say for your current case. Now, you want to then talk about your dark fringe. A similar reasoning could also apply. This one, I will need to draw it somewhere. Just let me try and see whether do I have enough spacing here. Okay, maybe I'll just write here on the left hand side here. So I'm just gonna erase this. This one, let me rewrite it. This one, V and F constant, therefore lambda constant. Okay, so I want to explain the part where you have destructive interference right over here. So for the part where you have your dark fringe, which is the result of destructive interference, you could likewise say that the waves from S1 and S2 will meet a dark fringe, but they meet 180 degrees out of phase. So let's just say, for example, I thought about wave from S1 meeting at this point, and the wave from S2 also meeting at this point to give me a dark fringe. They must meet 180 degrees out of phase. So in the case that they meet 180 degrees out of phase, it looks something like this now. Okay, so let me just try and draw it nicely. If they meet 180 degrees out of phase, you could have a case where your waves is like this for S1. So let me just draw it. This is the wave for S1 from source S1. This one again is an amplitude of A. And then for wave from S2, it also has the same amplitude, but is 180 degrees out of phase, like this. Okay, so it's 180 degrees out of phase in a manner similar to this one. So this one is also having an amplitude of A. So when they meet together 180 degrees out of phase, because they are meeting 100 degrees out of phase and they have the same amplitude, your resultant wave would be 0. Okay, your resultant wave would be 0. There's nothing there. So because there's nothing there, that's why you don't see any light. It's considered to be a dark fringe because complete cancellation has occurred. Now, in the event that you use an even larger intensity for the light, the waves from S1 and S2 again will still travel to this point here where you have your dark fringe, but the amplitude is again bigger, just like the case for constructive interference just now. But it actually doesn't make any difference for the end result later on, because you can see this happening now. If I have a larger amplitude of the wave right now as a result of larger intensity, because they still meet destructively or 180 degrees out of phase, and the amplitude still remains the same, complete cancellation still occurs. So this one, if I tell you, is again 1.5a, and then this one is again 1.5a. They meet constructively, they meet destructively, they still complete cancellation. So you're still going to end up with this. Okay, so this one, what you can say here is that even with larger intensity, this one I'll write it in red, even with larger intensity, complete cancellation of waves still occur. Okay, so because complete cancellation of waves still occur, therefore dark fringe remains unchanged. Okay, so here nothing changes, but for the bright fringe before this, it actually becomes brighter still. Okay, so dark fringe remains unchanged. This is the next change that you can see. And then there's another change also that you can also kind of mention. Because you're talking about a double slit, you see, they tell you here you have two slits. Now, we know that for double slit, the equation that you will always use is lambda is equals to ax over d. So if there are no changes to A slit separation, if there are no changes to A slit separation, wavelength, and D, slit separate the fringe spacing remains unchanged. Okay, this one here, if I rearrange it to give me fringe separation, this one is lambda d over A. If there are no changes to slit separation, wavelength, and the distance between the slit and the screen, fringe separation should remain unchanged. Okay, this is another possible, this is another thing that you can actually mention here for your answer, because they ask you what are the changes, if any, when you go and increase the intensity of light incident on the double slit. Okay, so for the part where they ask you describe the appearance of the fringes after this change, describe whether it's different or similar to the appearance before the change. They give you 3 marks here. Okay, they give you 3 marks here. You're supposed to say 3 different things. So I'll write it here. Let me just erase this. This one, I write it below here. Therefore, dark fringe remains unchanged. So for your answer, this one, you can say that bright fringe appears brighter, dark fringe remains unchanged. Then after that, you can say that fringe separation, which is your x, also remains unchanged. Okay, so these are the 3 possible answers to give you the 3 marks. So if you check the answer, they actually did mention that to you. The bright fringes are brighter, no change to the dark fringe, no change to the dark fringe, no change to the fringe separation or fringe spacing. Okay, so you need to mention all 3 of these to get your 3 marks. Okay, so that one is all right. Okay, then after that, I move on to part E. Now for part E, they mentioned this. Okay, for part E, the light of wavelength 660 nanometer is now replaced with blue light from a laser. Still explain the change, if any, that must be made to the separation of the two slits so that the fringe separation of the screen is the same as it was for light of wavelength 660 nanometer. So they want the fringe separation to be the same as before when you go and replace your light with a blue light. Okay, so let me just try and see whether I can squeeze in the answer, the workings on the screen. Now, if you remember the wavelength of visible light, maybe I write it here. Okay. You guys remember the wavelength of visible light? Wavelength of visible light is from 400 to 700 nanometer. Okay. And then after that, for visible light, you have those 7 different colors, Roy, G, Beef. And then going towards this direction is where wavelength decreases. So the smallest wavelength is actually going to be violet. This is 400 nanometer. The largest wavelength is actually going to be red. This one is going to be 700 nanometer. Okay, 700 nanometer is for red light. So now they tell you you are using blue colored light. Okay. The light before this, they never told you the color. They just told you that the wavelength is 660 nanometer. Then they tell you they replace it with blue light. So blue light is this part here. Okay. So the question here now is the blue light wavelength going to be larger or smaller than the 600 nanometer? So common sense would kind of tell you it's going to be smaller because you see, red light is already 700 nanometer. If you're talking about 600 nanometer, it's probably somewhere around here. This one is going to be for 660 nanometer. It's very close to 700 nanometer, right? So it's probably somewhere around here. This one is 600 nanometer. So blue light is a bit further off towards the right. So going towards the right is where wavelength decreases. You can actually say that wavelength of blue light is actually smaller here, okay, by using some common sense. All right, so I can say that wavelength of blue light is smaller. This is definitely one point you want to say. Now they want your fringe separation to remain the same as before, even though you decrease the wavelength of light. So here you can probably say something like this. If you know that lambda is ax over d, and then x is lambda d over a, you want x to be constant. So let me just rewrite this. X is lambda d over a. You want x to become constant. Okay. So if this one is constant, this one must remain constant. But right now, this wavelength is smaller. You need to make sure that whatever changes you made ensures that your fringe separation is the same. The change that you make must be opposing the wavelength decrease. Just look at the equation. If I wanted to make sure that wavelength is constant here, I can only change D and A. Change this one, X is proportional to lambda. So lambda drops, X would drop, right? Then X is proportional to D. And then after that, X is inversely proportional to A. So the thing now is that if my wavelength drops because I'm using blue light, my X is dropping. In order to counter that so that my X remains the same, I need to do some changes so that my X increases. So in my case, I can actually do something with D, I can actually do something with A. But I need to make sure that the change is opposing the decrease in wavelength, because the decrease in wavelength causes X to drop here. So I want the X to increase back so that it remains unchanged. So there are two things I can actually change here. For my case, I can actually say that if D increase, X will increase. And then for X inversely proportional to A, I can say that if X drops, X will increase so that X remains constant. So one of the things I can probably just say here is that in my case, if I want the fringe separation to remain the same, I would say that decrease the fringe separation. This one I will say decrease the slit separation, decrease the slit separation so that fringe separation remains unchanged. Okay, you can decrease the slit separation so that the fringe separation remains unchanged. So what did McKinsey mention? They just say shorter wavelength is for blue light, so you need to decrease the slit separation. But they didn't really mention why lah. So to really see why, you probably need to see it in this manner here. Because a decrease in wavelength will cause the fringe separation to drop. You need a change that is opposing it. So you look at what you can do with D, you look at what you can do with A to create an opposing change so that your X remains constant. Okay. The marking scheme didn't mention anything about the distance between the slit and the screen. Okay, it isn't inside. Oh, here you actually shouldn't mention any of it because the question did mention what can you do to the separation of the two slits. Okay, the question already mentioned to you, what can you do to the separation of the two slits? So in your case, they already single out what can you do to A. Okay, but if they didn't say that, you can actually mention the separation between the screen and the slit. Okay, so that is for this. Okay, this one is for the wave part. Then after that, I'll just clear off the screen and move on to 6A. Now, for part 6, question 6, you have a network of 3 resistors of resistances R1, R2, and R3 as shown. The individual potential differences across the resistors are V1, V2, and V3. The current in the combination of resistors is I, and the total potential difference across the combination is V. Show that the combined resistance R of the network is given by this. R is equals to R1 plus R2 plus R3. This is actually asking you to derive resistances in series. So you can actually write something like this. This one is from K2 law, Kirchhoff's second law. Sum of PD is equals, sum of EMF is equals to sum of PD, right? So you can actually say something like this. V is equals to V1 plus V2 plus V3, which in turn becomes IR equals to I1 R1 plus I2 R2 plus I3 R3. Okay, but because you're connecting the resistors in series here like this, if I tell you that you have I1 here, I2 here, and then I3 here, because they're connected in series, there's no chance for the current to split up. The current will remain the same throughout the 3 resistors. So this one, I can say this. From K1 law, I1 equals to I2 equals to I3 is equals to I itself, which is over here. So therefore, IR is equals to IR1 plus IR2 plus IR3 giving you R equals to R1 plus R2 plus R3. So this is shown. Okay, so that's for part A. So if you're okay with that, then I'll move on to part B. Okay, so part B is something else. This one, part B will be something like potential divider. Now for part B, a battery of EMF 8 volts and negligible internal resistance is connected to a thermistor, a switch X, and 2 fixed resistors as shown in the figure below. Resistance R1 has a resistance of 6 kilo ohm and resistor R2 has a resistance of 4 kilo ohm. So switch X is open, calculate the potential difference across R1. So if switch X is open, it will probably be better just to draw the diagram. If switch X is open, your circuit looks like this right now. Okay. With switch X open, I don't really need to bother about this. Okay, this part I just disregard it. Okay, with switch X open, I just consider the parts where current can actually flow. So this one, you will see that current is flowing like this. This one was 8 volts. This one was 6 kilo ohm. This one is 4 kilo ohms. Okay. This one is your R1 and R2. So let me just write it here. This is your R1. This is your R2. So they ask you to calculate the potential difference across R1. Basically, they want this. If you connect a voltmeter across R1, they want the voltage across it. So notice that in your case, you have at least 2 resistors and the same current is flowing through the resistors. You can actually use potential divider equation. So in your case, you can now say something like this. So V is equals to R1 over R1 plus R2 times your V in. Your V in is actually the 8 volts. So your resistor values would be 6 over 6 plus 9 times 8. You see, did I do something wrong here? 6 ohm and 4 ohm, sorry. 4 kilo ohms. I wrote this as 9, right? My mistake. This is 4. Okay. So 0.6 times 8 gives you 4.8 volts. All right. So the answer for this is 4.8 volts. Okay, then switch X is now closed. In part 2, the resistor of the thermistor is 12 kilo ohm. Calculate the current inside the battery. Okay, so in my case, if switch X is closed, this one I can actually draw it here. If switch X is closed, I have something that looks like this right now. Okay, this is what I have. Okay, and they already told me that the resistance of the thermistor is 12 kilo ohms. So if I try to write in all the values that I know before, this is R1, this is R2, this is my RT. The values will be 6 kilo ohm, 4 kilo ohms, and then 12 kilo ohms here. Okay, these are the values that you need to work with. And then your EMF still remains at 8 volts. They want the current in the battery, meaning to say they want this one. Okay, if current comes out of the battery, it flows like this. It will split up at this junction here before combining back and returning to the battery. Okay, so the current in the battery refers to this one. Okay, so to make your life easier, it will be easier for you to draw an equivalent circuit. You simplify the parallel connection right over here. You will get something like this. Okay, try to simplify the parallel connection. You should be able to get your current. So let me just draw this. So this one is R1 at 6 kilo ohms. This one is the resistance in parallel, which is basically this one here. This one will be 1 over 4 plus 1 over 12 power negative 1. It's going to be 3 kilo ohms. Okay. So from here, if you again want to simplify it, if I want to simplify the circuit even more, it becomes like this, where this one is 8 volts, this one is 9 kilo ohms. Then same current is now flowing. Okay, so in my case, I need to find out my resistance in parallel first. I need to show the working, because if I'm not mistaken, the question wanted you to show that. Yeah, sorry, the answer scheme wanted you to show that. So you just show those workings accordingly. So I would just say the resistance in parallel, I already show it here, is 1 over 4 plus 1 over 12 power negative 1, giving me 3 kilo ohms. Then after that, if I apply V is equals to IR, my V is 8, my current is what I want to find, my resistance is actually 6 plus 3. This one is 9 now, okay. This one is 9. So I is going to be 8 divided by 9, giving you 0.889 amps. I forgot one thing, sorry. I forgot the kilo ohms. You have 9 kilo ohms, so this one is 10 power 3. Okay, so your current is going to be 8 divided by 9 divided by 10 power 3. It's going to be 8.89 times 10 power minus 4 ampere. Okay, let's see whether it's correct or not. Okay, so this is correct. Okay, then there's this last part to your question. All right, just give me maybe 5 minutes just to finish this one off. Okay, sorry for running over the time. Now, switch X in the circuit B remains closed. The temperature of the thermistor decreases. By reference to the current in the battery, state and explain the effect, if any, on the decrease in temperature on the power produced by the battery. Okay, so there are a few things here to note. They tell you temperature of the thermistor decrease. They want you to make reference to the current in the battery, and then subsequently explain what happens to the power produced by the battery. Okay, so this one is worth 2 marks, if I'm not mistaken. Okay, now let me just see this. 3 marks. Okay, first thing you can probably say here is this. When temperature decreases, thermistor resistance increases. Okay, this is one thing that you have learned for thermistor. For thermistor, when temperature drops, resistance of thermistor increase. And the converse will also be true that if temperature increase, resistance of thermistor drops, because it follows a graph that looks like this. RT versus temperature is like this. Okay, so when temperature decreases, thermistor resistance increases. And then after that, what can you then say? your total resistance actually increases. So your total resistance increases, plus current decreases. Okay, when your total circuit resistance increases as a result of thermistor resistance increasing, your current will decrease. Okay, thus current decreases. So power produced by a battery, if you're talking about power produced by a battery, P is equals to EI. Since E remains constant, P is proportional to I. Okay, so this then means that therefore when current decrease, power produced by battery decreases. Right? When your current decreases, your power produced by a battery decreases. All right. So your points will be this first sentence, this second sentence, and the fourth sentence here. The third sentence here, since P equals to EI, since E remains constant, P is proportional to I. This one is probably not something that will be given any mark. Okay. The P equals to EI here refers to power produced by battery. Okay. So if you want to check the answer a little, let's just have a look at the answer. So here they say thermistor resistance increase, this is the first point. So total resistance increase, so current decreases. This is another point. And then after that, straight away they say P equals to EIE constant, so power decreases. Okay, so it's the same thing as what I just wrote here. For the last question, you have a nucleus of cesium-137 that decays by emitting a beta minus particle to produce the nucleus of an element X and an antineutrino. The decay is represented by the given equation here. State the number represented by each of the following letters, P, Q, R, and S. So this is a nuclear reaction. In any nuclear reaction, we know that the proton number and nucleon number must be conserved. What this means is that the proton number before and after the reaction must be the same. Okay. The same could also be said for the nucleon number. The nucleon number before and after reaction must be the same too. Okay. So we try to apply the conservation of proton number as well as the conservation of nucleon number for the given equation here. But let's just single out some of the particles here, specifically the beta minus particle that we are seeing here. Now for a beta minus particle, we already know what is its proton number and nucleon number. The beta minus particle would have a proton number of -1 and a nucleon number of 0. So right now, we already know what is P and R. P would actually be 0, and then R would actually be -1. So from here, we can then work out what is the rest of the numbers for the other letters. So in our case, this one is 0, this one is -1, okay? So if we want to work out what is the numbers for letters Q and S, we can actually just sum out the proton number and nucleon number. Now, if we just look at the proton number itself, before the reaction was 55, okay? So here we have 0, and then we have -1. What should be the number for S in order for us to get back 55? It should be 56, isn't it? So in our case, if we want to write some sort of reaction here, if we say proton number conservation, in our case, it is 55 equals to S plus -1 plus 0. This is letter S, sorry, it's not 5. So S is actually 56. So letter S here now is 56. Then after that, we look at the nucleon number. This is 137. So the rest of it for beta minus particle was 0, and electron antineutrino was 0. So Q here ought to have been 1372, isn't it? So let's just write some remarks here. If we talk about nucleon number conservation, before the reaction it was 137. After the reaction we have Q plus 0 plus 0. So Q would be 137. So 137 for Q. Let's check the answer. It will be 0 for P, 137 for Q, and then after that R will be -1, S would be 56. Okay, so we have the correct answer here. For the next part of the question, state the name of the class or group of particles that includes the beta minus particle and the antineutrino. This one we know is going to be our lepton. All right, because if you're talking about beta minus decay is neutron changes to a proton, giving you your beta minus particle and your electron antineutrino. Okay, so your leptons are actually these two particles right over here. Okay, so that one is for this. Let's check the answer again. It is leptons. All right, now then you move on to the next part of the question. You have particle Y that has quark composition of DDD, where D represents a down quark, and then particle Z has a quark composition of U bar D, where U bar represents an up antiquark. Show that the charges of particle Y and Z are equal here. So in our case, if we're talking about the charge of an up quark, it will be +2/3e. But if you're talking about the charge of an anti-up quark, it will be having an opposite sign but the same magnitude of charge. Okay, and then when you're talking about the charge of a down quark, it is actually just -1/3e. Okay, so these are all the charges relevant to your current question. So for particle Y, the charge of particle Y would be 3 Ds, okay, 3 down quarks added together. So it's -1/3e plus with -1/3e plus with -1/3e. In the end, giving you an answer of -e. Okay. Now, if you then move on to the charge of particle Z, which consists of an up antiquark and a down quark. So an up antiquark would be -2/3e plus with the charge of a down quark is -1/3e. You're going to get back the same answer as -e. All right. So looking at these two charges now, therefore, Qy and Qz are equal. All right. Then moving on to the last part of our current question. State and explain which particle is a meson and which particle is a baryon. Okay. Now, last time we would have learned that hadron is just simply a group of quarks. As long as you see a group of quarks, that one would actually be our hadron. Okay. But there's actually a more specific classification for group of quarks, namely your meson and baryon. Now, meson is actually a pair of quark and anti-quark. Okay, and then when you're talking about a baryon is just simply a group of 3 quarks. Okay, so in our case, we need to explain which of the particles that we have above is actually a meson and which one is actually a baryon. So in our case, if we talk about a meson is a pair of quarks and antiquark. So we will say that meson consists of a pair of quark and antiquark. Therefore, particle P, sorry, not particle P, therefore particle Z is a meson. Because you can see that it consists of a down quark and an up antiquark. There is a pair of quark and antiquark there. So therefore, particle Z is actually our meson. Okay. And then for the last one, baryon, we can say that baryon is a group of 3 quarks. It is a group of 3 quarks. Therefore, particle Y is a baryon. Okay, so that is how we would do this particular question. All right. Now, before I end this, just know that hadron, being a group of quarks, is actually just a more generic definition for groups of quarks. But when you're talking about meson as well as baryons, these are actually more specific definitions for the groups of quarks, because they will specify for you what type of quarks do you need to have and how many number of quarks do you need to have. All right.